So now we're back. We're going to do another example. So here we have the winner of the 2012 Tour de France. Average, I think it should say average, sorry, somewhere got lost along the way. Averaged more than 11 meters per second. And we're measuring some sort of average ballpark force to keep them moving. About 30 newtons of force, overcoming wind resistance and any sort of frictional forces along the way to keep them moving. We want to answer a couple of questions. How much power is that person's body having to supply to move them forward at 11 meters per second with 30 newtons of force? And then we want to answer another question. If the race is 3,500 kilometers, how much energy did the winner use to do this? So winner of the 2012. So you're looking at the power. If you want to draw your picture, I'm not very good at drawing bicycles. Kind of looks like a deer on wheels. Hold on. You've got somebody riding a bicycle. They're having to supply 30 newtons of force, and they're maintaining an average speed of around 11 meters per second. Okay, that's it. Speed's going to be in the direction of motion, and we're assuming that the force is going in the direction of motion as well. Okay, so it's at 30 newtons of force going forward. Okay, so the power, right? It's equal to the change in work over change in time, dW dt, which we represented in the last one, force dotted with the velocity. But they're in the same direction, so it just becomes force times velocity, or 30 newtons times 11 meters per second, which gives me 330. Newton meters per second, or joules per second, or watts. Okay. So that's the power. They have to supply this 330 watts of power to keep moving along the way. Okay. Part B, if the race is 3,500 kilometers, how much energy do they use? Okay. So we had this relationship. Power is equal to the dW dt, or the change in energy over change in time. We're trying to find out how much energy it costs or how much work they have to do. So we could rearrange this to say that the energy that is required is equal to the power times the amount of time that's going on. The power we know, 330 watts. What we need to do is find how long it takes. Okay, let's think about what we know. We know how long the race is, 3,500 kilometers. We also know how much force that takes, but that's not going to help us. But we know how fast they're moving, okay? And we've got the average speed. We don't have to worry about acceleration because while the person's speed goes up and goes down, they're averaging this 11 meters per second the whole time. So you get that 3,500 kilometers is equal to about 11 meters per second times the amount of time that it takes. Delta x is equal to the average speed times delta t, or delta t is equal to delta x over v average, right? 3,500 kilometers divided by 11 meters per second. So the total energy, how much has to be used, is equal to the power, 330 watts, times the distance divided by the average speed, which is equal to 330 watts times 3,500 kilometers, but be careful. You got to use proper units. So 3,500 kilometers, we need to get that into meters. So 3,500,000 meters over the average speed, 11 meters per second. Plug that in, and we get 1.05 times 10 to the 8 joules, okay. Which, or about 0.105 gigajoules. Okay. Use some of our prefixes inside of there. All right. I double checked this, so I was just sort of curious what happens, and Googling, it looks like the Tour de France people burn about 6,000 calories a day, and the race takes place over 23 days. So this calculation, it actually lowballs it. So they're not burning 1 times 10 to the 8th. There's another factor of 5 on top of it. It's because the bodies are inefficient, right? So nothing's going to be perfectly fighting off the air resistance and all of those things. They're having to supply, they're burning more calories in what they're eating to get their legs moving to overcome these forces inside of there. So you actually get about 0.5 gigajoules in all. All right. And here, here's another question that we're not going to do, but I'd like to pose it to you so you think about it. Where there's a 1,500 kilogram car, it's got a front profile, right? A length and a height, and it's trying to move this whole thing through it along the way. And there's some sort of coefficient of rolling friction that the car is having to fight. Okay. What power must the engine provide to drive at 30 meters per second if 25% of the power is lost before reaching the drive wheels? Okay. So you have a lot coming into place in this one. You could come up with a value of the friction that has to be overcome. Coefficient times the normal force in that case. There's also, the reason we're not doing it is that there's a drag feature in here, right? So you're moving this area through the air, and it costs a little bit of force to move that as well. Okay? So you could calculate that, and then you've got a speed, but then you also have to account for energy losses inside of the engine. Okay, it provides energy, but then there's frictional losses. There's fundamental losses that we'll get to. So there's just a ballpark loss of 25% inside of this one. So you could try to think about how much power it has to do. Okay? A little bit more than if it was a perfect engine. Okay. All right. So let's recap this chapter. Here we had a system. The system had multiple types of energy: kinetic, potentials, chemical, and then could be thermal losses as well. And overall, you can add energy to the system in any one of those forms by doing work on it, or you could lose energy by having it do work, or apply a force opposite the direction of motion. And later on, we'll add in our heat. And this led us to this work energy theorem, where the change in energy is equal to the work. All right, and then we'll talk about this one in a little bit. Excellent.